Hey, in this video I'm going to discuss an article I came across on CSI's Knowledge Base. It's titled Effect of Rigid Diaphragms on Buckling of a Cruciform Structure. Now, as the name suggests, it's the analysis on a rather odd-looking structure with all shell member makeup. The author compares the analytical results of three different versions of the same model with different treatment of force, implant stiffness. One with rigid diaphragm constraints, one without, and the third one with diagonal stiffness terms multiplied by 1000. It's called a stiff version. Now, the buckling analysis under self-weight load alone. As you can see here, the buckling factors and mold shapes. Now, the striking difference is that rigid diaphragm constraints seem substantially lower the buckling factor of the torsion buckling mode. Now, the author experimented further with the model by setting Poisson's ratio to 0 in the rigid diaphragm model, and since the result come back almost nearly identical to the stiff version, he concluded the so-called Poisson's effect sustained by infinitely stiff horizontal diaphragm constraint is behind the discrepancy in the analytical results. Now, I personally find that conclusion rather vague and unconvincing. So I did a little study myself, and I will offer my humble opinions. Now, by observing the stress plot the author provided in the article, we can see that the wall members are not matched. And this is important. This is a wall element strain-stress relationship. The CSI's analysis reference say that static combination is used to simplify the relationship from this one to this one. And with the three strain component being 2 axial strain and 1 shear. Now, in the rigid diaphragm model, due to the fact that the wall members' top and bottom knots are constrained respectively on the level, the horizontal strain should be 0, while the horizontal stress, on the other hand, is equal to this, and it's by no means 0. Well, in the flexible model, due to the fact that these two terms are opposite signs, so they tend to cancel each other out. So the horizontal stress will be close to 0 for most of the wall elements. I think this is the essence of the Poisson's effect in the rigid diaphragm model, where the presence of unignorable horizontal stress under vertical load alone. Now, it's worth noticing that for the stiff version, although the horizontal stress is so smaller than the flexible one, shouldn't be 0. So, like the flexible model, it shouldn't be very large, very pronounced horizontal stress. Now, also should be noticeable is that in the rigid diaphragm model, the shear strain, due to the fact that horizontal strain is 0, will be missing this part. So it will be smaller than in the flexible model. Now, buckling analysis can be seen from an energy perspective. When buckling happens, the strain energy of the buckling mode, UB, should be equal to the structural strain energy under the buckling load vector, U sigma, multiplied by the buckling factor, lambda, i.e. UB should be equal to lambda times U sigma. And this is the equation for U sigma. Apparently, the presence of this horizontal stress component in the rigid diaphragm model increases strain energy under the buckling load vector. Now, with smaller strain values, UB and U sigma should both decrease in the rigid diaphragm model and the stiff models, presumably on a similar scale. By setting Poisson's ratio to 0, though, the horizontal stress component is eliminated in the stress matrix. This may explain why at 0 Poisson's ratio, rigid diaphragm version is so close to the stiff version. Now, UB may change on different scales for different buckling modes. Now, let's take a look at those buckling modes. First of all, the bending buckling mode, the slabs are in transitional movement. This is a more likely buckling mode under self-weight load because the wall elements have relatively easily distributed strain energy. Now, it's interesting to notice that the buckling is along the 45-degree direction instead of the principal axis. This I personally believe it's because the building is the weakest along that direction. And if we take the building as a whole, as a structural section, its second moment area will be equal to this when it's rotated an angle alpha. And set the partial over alpha to 0, it yields 45 degrees. Now the torsion buckling mode, the slabs are in rotational movement. The wall members on the outermost side of the building will have substantially larger strain and hence strain energy than their inner ones and the outer plane ones. Now this feature makes it an unlikely buckling mode and an evenly distributed load vector. Now due to the fact that the strain energies are concentrated, I think the UB will decrease more in this buckling mode than in the bending buckling mode when the strain value decreases. Now this is a table I made to compare the strain energy change in different modes when the strain value decreases as compared to the flexible model. Now when strain value decreases, the UB should drop moderately for bending mode, or drop heavily in the torsion buckling mode, while U sigma should drop moderately for all versions of the model, except for the rigid diaphragm normal potence ratio model, where that additional horizontal stress component will increase its value, and the buckling factor will change accordingly. Now, the discussion above are based on some rough analysis, theoretical analysis, with some surmise. It's not backed by any quantitative studies, so there still could be errors and inconsistencies. But I think I still want to share some lessons I learned from this article. First, caution needs to be taken when adding constraint of any kind to a structure, especially to degree of freedom of interest. The math behind the analysis should be studied and understood. Now, second, the elements that have common laws with the constraint elements should be matched properly. Such as in this example, if the walls are matched properly, they should be less affected by the absolute zero generated by the rigid diaphragm constraint. Now, third, the finite element method can be challenging for structural engineers because it has its own intricate body of theories and methods. Now, it's not like one of the special purpose softwares where you just tick a few boxes and it seems like the software will take care of everything for you. Now, those softwares reduce engineers to drivers in a driverless car. It's an oxymoron and an irony. But I believe that engineering principles and basic theories are indispensable parts of good engineering work. Thank you for watching this video.